Okay, second part of 5.1 acid-base concepts. In this video, we'll be looking at, well, second box in a student intended learning column. We're looking at writing equations showing proton transfer between an acid and base, as well as identifying the conjugate acid-base pairs given the equation for proton transfer reaction. So we'll look at equation and what's called conjugate pair. Okay, so chemical equations, there you go. All right, so what is conjugate pair? So conjugate pair is two species which differ by a proton. For example, HCl, so hydrochloric acid, if it gives off its proton because it's an acid, it will leave Cl minus. So HCl and Cl minus, they are conjugate pairs. They're in pair. Where HCl was an acid, its conjugate base Cl minus. Now we say base because if you remember the Lowry and Bronsted definition, a base is something that can gain or accept proton. So Cl minus can gain proton to become HCl again, which doesn't really happen, but that's why it's called conjugate base, not conjugate acid. So HCl acid, conjugate base of that is Cl minus. Consider the following reactions. So, well, let's write it down as an equation. So hydrochloric acid and water, that's what you are trying to react. You get chloride ion, hydronium ion. Let's also identify what is conjugate acid and base, or base and conjugate acid of it in this equation. Oops, sorry, there's another equation there too. Ammonia and water. So when you react, let them react. Which one would be base acid, and conjugate base? All right, firstly, hydrochloric acid and water. Now, hope you know that when they react, one will be H3O plus, and also Cl minus. So they are the products if you look at the forward reaction. In acid and base, sometimes you see this two-way arrow. That's to show that the equation can go back. Not to say that which is stronger, or in this case, because acid has got tendency to give off and water is very neutral, so majority of reaction would want to go forward, but some reaction might want to go backwards. If you draw the shape of it, you would also notice in here that it has the oops, use different color for hydrogen, for proton here. It has got coordinate bond, and this hydrogen can come off from H3O plus anytime. So this is considered to be acid if you are looking at backward reaction. Now, firstly, HCl was acid, and now we were saying that this is something that's considered to be acid, but it is a conjugate acid of H2O. Do you see that? H2O used to have just H2O. Now it has got one more proton. So species which differ by one proton. What do we call that again? If this was a base, then this would be conjugate. Conjugate. How about that? Conjugate. acid. Hence, this one will be a conjugate base of HCl. Conjugate base. So, which one is a pair? HCl and Cl minus, they are one pair. And H2O and H3O plus, they are the other conjugate pairs. Let's look at the other example, which was ammonia and water. Okay. Now, let's just identify what's what. Ammonia is something that can accept proton, so this will be a base. Now, if one is base and if something is donating proton, water is now acting as a acid. As product of the forward reaction, what you would expect is NH3 plus one extra proton, so NH4 plus. Now if you draw it out, that would look like NH, H, H with an arrow, because that's a coordinate bond. As a whole, it has a charge, NH4 plus that is, and you would also get water with one less of hydrogen, so OH minus. If you look at this pair as reactant for the backward reaction, OH minus here would be an acceptor of a proton, so this will be considered as base. This is the conjugate base. And that's an acid and base pair, conjugate acid base pair. And NH4 here is going to be conjugate acid, because NH4 plus can donate this proton to this conjugate base and then can form the base, original base, which was ammonia. Let's just draw the arrows around. Original acid, that became this. So species that differ by one proton. NH4 plus and NH3, they also differ by one proton. So they are the concept of conjugate acid and base.